So organic compounds. Early chemists divided compounds into two categories, organic and inorganic. Organic came from living things and inorganic came from non-living things. Organic compounds were easier to decompose. You can burn them. Inorganic compounds are difficult to decompose. They found that it was hard to synthesize organic compounds, but it was easy to synthesize inorganic compounds. And so they had these two broad categories. We do still use those categories today. And, it's just an illustration of how words in everyday language don't always have the same exact meaning as they do in science. When a chemist says an organic compound, that does not mean that it's pesticide-free and totally safe. Because really, is anything totally safe? No. Oxygen and water are necessary for life, but too much of them will kill you. Everything is made up of chemicals, and so you can't have something that's chemical-free. Now, there are chemicals that are bad for you in small quantities even, but organic does not mean safe. In fact, a chemist would say that organic things are probably more dangerous than inorganic. Today we define organic compounds as compounds containing carbon and hydrogen. They sometimes have a little bit of other elements in them, but they're predominantly carbon and hydrogen. The key element is carbon. And now we can synthesize these compounds in the lab very easily. So here's an example. This is methane. We just looked at its combustion. It's got carbons and hydrogens. It's an organic compound. Carbon is a nonmetal, and so it forms covalent bonds. And it always forms 4 covalent bonds. Could form 4 single bonds, 2 double bonds, a single and a triple, a double and 2 singles, any combination. It will form bonds with other carbon atoms as well as with other elements. And the reason that this organic chemistry, the chemistry of carbon, is so complex is that the carbon is able to make long chains of carbon atoms with other things attached. And those chains can be straight, they can be branched, they can be in rings. And so there's a lot of different combinations just with carbon and hydrogen. Here's some examples. Here we see propane. Propane and just has single bonds. It's all carbons and hydrogens. Here's isobutane. This has the same, This is isobutane. Here's cyclohexane, where we have the carbons, like they're playing Ring Around the Rosie, and the hydrogens are hanging off the sides. And then here we have some with multiple bonds. This has a double bond. This one has a triple bond with the carbons. Here we've got one that has some oxygens in it. But this is primarily carbon and hydrogen, and so it's still considered an organic compound. If you notice in all of these, if you count the lines coming from each carbon, they all have 4 lines. Here, this carbon has a triple bond with another carbon. That's 3 lines, and 1 line, 4. So carbon always makes 4 bonds. We can organize the organic compounds into hydrocarbons and functionalized hydrocarbons. So the hydrocarbons are just hydrogen and carbon. Functionalized hydrocarbons may contain other atoms, most commonly nitrogen and oxygen. Hydrocarbons are very important in our society. Most common fuels are hydrocarbons. Oil, gas, propane, gasoline, all of these things are hydrocarbons. And when they burn, they form carbon dioxide and water and a lot of energy. So we're just going to touch a scratch of the surface of learning how to name these. So in organic chemistry, we use a suffix to indicate how many the prefix is how many carbon atoms are in the molecule, and the suffix tells us information about multiple bonds. So if we only have single bonds as a category, these are called alkanes, and the suffix there is -ane. If we have double bonds, those are alkenes, and we use the suffix -ene, and alkynes have at least one triple bond. So we've got a base name followed by a suffix. The base names, the first four are a little different than those other prefixes that we learned. After that, they're very similar. So when we get to 5, pent is for 5, hex is for 6. We learned penta for 5 for the molecular compounds. So once you get to 5, it's all the same, but these first 4 are kind of strange. Meth, eth, prop, and bute, methane, ethane, propane, butane. It's sort of historical why it is that way. Kind of hard to remember. So, Mom eats pickled bananas. That's how I remember. And I say this in my head when I'm trying to figure stuff out. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons. The ones after that make sense. And then we've got these as our suffixes. So we could have octane, we could have ethyne, we could have pentene. So we take the prefix and the suffix, or the base name and the suffix, and put them together. Here's some examples. So here's methane. Meth meaning 1 carbon, ane, and so here we have 1 carbon, it has only single bonds, and those bonds, we put enough hydrogens on there that all the carbons have 4 bonds. Here's propane. Mom eats pickled, so propane is 3. This is 3 carbons, and all single bonds because of the ane. This is N-butane. Butane, 4 carbons. So here's the 4 carbons. Now things get a little more complicated here because these 4 carbons wouldn't have to be in a straight line there. They could make a branched structure, and so then the names get a little more elaborate. We're not going to go there. N-pentane. N just is standing for normal or give you the straight chain. So this is pentane. Here we have ethene and ethyne. Ethene, 2 carbons, double bond. That's what the ene means. Ethyne, 2 carbons with a triple bond. The functional groups are so called because they are specific combinations of atoms that cause the function or the behavior of that compound to be different. A double bond or a triple bond could also be called a functional group. When we have a group of compounds that have the same functional group, we call them a family. Methanol and isopropanol are both members of the alcohol family. So the alcohol functional group is this OH. And so here's methanol, meth, it's got 1 carbon. Here's isopropanol, that prop prefix is 3 carbons. So here's 3 carbons, and it also has an OH group. That's the functional group. Here's a table just giving you the main categories. So alcohols, they're going to have this OH functional group in them. There's ethers, aldehydes, ketones, carboxylic acids, esters, and amines. Carboxylic acids and amines, yeah, I think those are the 3. Those are the three families that I would like you to be able to recognize. So we recognize these alcohols, we're going to see an OH group. Carboxylic acids, these are very common organic acids. Malic acid, there's acid in fruit, citric acid, those are all carboxylic acids. Here we have an OH group but also on that same carbon we have a double bond with an oxygen. And then amines are very important. They're very important in your DNA. And these have nitrogen in them. So we've got this NH2. So we can think of this as being a substituted ammonia molecule. Ammonia would be NH3, and here we're putting some carbons and hydrogens in there instead of a hydrogen. So I want you to be able to recognize those three categories. So if I gave you an example, like if I gave you this, you should be able to tell me that that's a carboxylic acid. Some extra examples. Let's draw the structural formula for nonane. If I asked you to do this on an exam, it's not specifying what the chain looks like. The simplest thing is to just make a straight chain, but I would accept anything that has the correct number of carbons and the right kind of bonds. So nonane has how many carbons? 9. So we need to put 9 carbons in there. Easiest to just put them in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I have to put hydrogens on them. Each carbon needs 4 bonds. So this works out nicely with, like north and south, east and west. I can just put 4 bonds on each of these carbons. Each line represents a bond. And I can't put any carbons in because I already have the 9. The rest of it's just going to be hydrogens. And so this isn't difficult, it's just tedious making all these H's. And there's a reason that we have more abbreviated formulas for these things. And this is the sort of math that you get in organic chemistry. We had to count the number of carbons. They won't be harder than this on the next exam. It could be, I'd probably give this as a multiple choice, and so I'd give you 4 or 5 structures and ask you which one is propane.
This one exam 2?
Exam 2. Everything I'm talking about today is on the next exam, not exam 1. We finished exam 1 material last week.
We need to know the shape of this, right?
No. Mm-mm. And then I'm going to change this example. To which family does this compound belong? Alcohol is a reasonable guess. There's an OH group, but there's also the double bond with the oxygen. It's a carboxylic acid. It is okay to write the OH like that because the oxygen is actually what's bonded to the carbon. Yeah. So organic chemists have a very special way of writing their letters, and it's to convey connectivity. And it sometimes looks strange when you're new to it, but.
What you had before,
Mm-hmm.
before you placed the OH, on the mastering, I was doing it, I did say carboxylic acid. I was like, okay, fine. They told me ketone, I'm like.
Yeah, this is a ketone because the carboxylic acid has to have that OH group. And here there's no OH group. This is just all carbons here, and we have this double bond oxygen on a carbon, but there's no OH. And so if we go back and look at our groups here, our families, that's going to be this one, where we have the CO functional group, and there's carbons on both sides of this carbon. So that's a ketone. This is very similar but there's a hydrogen here, and that's an aldehyde. And if you're interested, the way I remember that is aldehyde has an H in it, and this has an H on that carbon. And ketone's the one in the middle.